Tēnā koutou. My name is Craig Ford. I'm a plant propagation research scientist at Scion. Thank you to Forest Grows Research for the opportunity to present to you today. I'm presenting work completed by our Scion Research Nursery team. The aim of this talk is to present evidence for new approaches to nursery propagation, which will allow New Zealand to supplement our production of Pinus radiata outside of its normal bare root production and planting windows, while also responding to a changing operating environment. New Zealand has a proud history of rising to nursery challenges. During the mid-1990s, the forest nursery industry was able to quickly ramp up production of radiata pine to meet the high afforestation demands of the time, between 40 and 75,000 hectares per annum. This was almost exclusively produced as bare root crops, as shown in the picture, and also led to a flurry of research and publications. After an almost 20-year maintenance period, we are once again challenged with high afforestation demands. The Climate Change Commission recommends we establish an additional 22 to 26,000 hectares of exotic trees over the next 15 years, with an ever-increasing addition of native trees, shown in green on the graph, until we reach an approximately 50,000 hectares of new forest per annum between 2028 and 2032. How much of that green gap is taken up with natives versus exotics remains to be seen. The mid-2010s planting stock demand was easily accommodated by our national nursery infrastructure, then producing around 45 to 50 million trees per annum. By 2018 and 2019, this all started to change, with the introduction of the government's 1 billion tree program. Within a very short period, nurseries were required to ramp up radiata seedling and cutting production to around 90 million plants per annum for 2019 and 2020, and could exceed 100 million plants in 2021. The question is, how can we sustain this production and establishment rate with some of the industry challenges we face, especially if, as has happened to date, radiata is required to fill the gap in our afforestation goals, in the event that native trees aren't produced in sufficient number. While bare root is the predominant means of deploying radiata, there are a number of new pressures on this industry that weren't as prominent in the 1990s boom. Some of these pressures include increasing pest and disease threats, coupled with tightening chemical legislation and social license to operate. As these pressures increase, it is becoming more difficult to raise bare root crops. The picture on the right-hand side illustrates a crop produced in the USA without fumigation in the foreground and with fumigation in the background. The health differences are pronounced. While significant effort is being put into improving sustainability in this system, there is also a widening opportunity to introduce containerized stock, where containers are temperature or UV sterilized and growing media is not reused. One of the main limitations of bare root production systems is the high seasonality of the operation, with lifting, setting of new cuttings and field establishment all happening within a short 3 to 4 month period in winter. Finding labour to do these exhausting menial tasks over this cold and wet period is difficult. Changes in legislation and environmental pressures are driving the industry towards a more high-tech, precision-based nursery sector, where we can limit or eliminate the application of harsh chemicals, use integrated pest management approaches, reuse water and nutrients, and improve our biosecurity measures. While technologies like these do exist and can be adapted to bare root forestry, like the weeding robot pictured here, containerized nurseries are significantly more advanced in this area, and many of the required changes are already very well understood and developed throughout general horticulture. Using containerized planting stock provides further benefits when it comes to labor supply issues. By having a year-round production facility, containerized nurseries are able to offer more permanent positions for staff with improved working conditions. Containerized nursery stock also allows well-established mechanization and automation opportunities for the nursery and for outplanting, thus requiring less staff which are more skilled. To ensure that we can meet our afforestation aspirations with these limitations in mind, we need to improve and expand alternative nursery systems to supplement the current bare root capacity. Over the past few years, Scion has been investigating new systems to meet some of these needs. Firstly, we have implemented trials looking at a modern containerized forestry nursery system widely used in South America and South Africa, where we are able to raise, harvest and set radiata cuttings all year round. This is commonly called a mini hedge system. Secondly, we have revisited how containerized trees perform against bare root crops out of the normal establishment window in a simulated field establishment trial. Knowing that mechanized planting can be hard on containerized stock, we have also investigated the feasibility of new paper pot planting stock to address this potential issue. Hydroponic mini hedges were originally pioneered in the early 2000s in South America for clonal eucalyptus production, but now dominate the cutting sector in South America and South Africa, including for pine propagation. By enclosing hedge tunnels and providing optimal nutrition, you are able to maintain year-round production of highly juvenile shoots, which show excellent rooting success and good root architecture. The system also allows for the recapture of water and nutrients, which can be UV sterilized, filtered and reused. Pictured on the right are examples of mini hedge sandbeds in South Africa, producing Patula Techonomania hybrid crossings. Sappi Forests is currently deploying approximately 60 million containerized trees per annum from their nurseries, with almost half being rooted cuttings. Some South American nurseries individually deploy 50 million or more containerized cuttings per annum, almost all of which are in paper pot or are transitioning to paper pots. Pictured on the left-hand side here are trial mini hedges for radiata at Scion, which were established in 2020 and have performed exceptionally well thus far. In our radiata rooting trial, we set cuttings monthly for 8 months, outside of the normal bare root season, across 8 different genotypes. All cuttings were set into 4 centimeter Elipot paper pots of around about 125 cubic centimeters volume, which is the equivalent of a TS48 container. Results presented here are for a total of 52,000 cuttings which we set at Scion between August 2020 and March 2021, for which we have final rooting and dispatch counts. While hormone, growing media and paper type trials were also conducted, these are not reported here. For this report, we look at rooting across months and genotypes. Rooting was highly favorable across all planting months, where the minimum success was 84% in January and February and as high as 98% in November and December. Despite the fact that previous bare root research has shown a high degree of variability in rooting success between radiata genotypes, there was no significant differences between genotypes in this trial, where the lowest overall rooting was 88% and the highest was 96%. Our conclusions so far are thus that radiata is highly amenable to the hydroponic mini hedge system of propagation, and year-round propagation success can be achieved even through summer. With learnings from radiata propagation technologies being implemented in South America, we chose to use paper pots, which performed well in the nursery and allowed for much easier lifting, packing and transport. Our second trial investigated the use of containers to extend our planting window. To test this, we established a field trial at Scion, where we planted bare root, standard containerized, and various paper pot options at monthly intervals, starting in the beginning of the very dry and hot March 2019. To illustrate the opportunity of raising cuttings quicker and out of the normal season using containerized growing, all cuttings were placed in November 2018, meaning that at the first planting in March, most of the cuttings were just 4 months old from setting. The exception to this was the winter set bare root control, which was set in June 2018 and was hence 9 months old in March. The container types used in this trial to compare against the November and June set bare root were the Transplant Systems TS48 tray and the Hyco V150 tray with paper pot sleeves shown in the middle photograph, noting that we did not yet have the proper holders for these in the country. Paper pots were sourced from 3 different companies: Plant Paper, BCC and Illipot. The picture on the far left shows a 7-month-old cutting in a paper pot. The results presented here are a combined measure of the survival and growth of treatments at 2 years, measured as the total conical volume for the plot of 6 trees. As expected, survival and growth of the winter set bare root cuttings was highly seasonal, as illustrated by the red regression line on the graph. Despite being 5 months older than the other treatments, the June setting still performed poorly outside of the recommended planting window. In comparison, the November or spring set bare root cuttings performed poorly all round, especially outside of the June-July planting window. The TS48 plugs, however, did significantly better than all of the November bare root cuttings of the same age. The poorest performance of the TS48 container type was in March, where at just 4 months after setting, poorly consolidated plugs experienced quite severe transplant shock and survival was poor. The paper pots, represented here by the Illipot VP paper, also showed significantly better survival and growth compared to the November set bare root cuttings, but significantly outperformed both the bare root and the TS48 treatments when established in March. This suggests that the plug, being held together by the paper, has reduced the transplant shock and facilitated better establishment. This trial has reinforced our understanding of the bare root crop cycle and its seasonal limitations, but has also illustrated that, as has historically been suggested, containerized plants offer an opportunity to extend this planting window. This trial has also shown that there is an opportunity to successfully root cuttings outside of the normal production window and still have them ready to plant within about 6 months, with good establishment results. This has huge implications for an investment in a containerized facility, as double cropping reduces the required growing area and hence also the capital costs of such a nursery. While further work is required on refining paper pot recommendations, it certainly shows great promise in being able to improve survival of younger plants on harsh sites. Future work should extend our understanding of nursery and field mechanization opportunities and requirements from plugs, and shorten our crop cycles in the nursery. A special thank you to the fantastic Scion Nursery team for growing, establishing and measuring these trials, especially to Bina Poi for the coordinating of the initial establishment and measuring, and Alex Lloyd for recent measuring and data collection. Special mention also to our science leader at the time, Heidi Dungy, for her support of this work at our nursery. Thank you. I welcome any questions in the question and answer section at the end of this session.